Previously, we've looked at how bodies move when forces are applied to them. In this video, I'd like to look at bodies that remain stable when forces or torques are applied. This is called equilibrium. For an object to be in equilibrium, two things are required. First, linear momentum, P, has to be constant, and angular momentum, L, has to be constant. In addition, if there are no translational or rotational motion present, the body is in static equilibrium. And in that case, the linear momentum isn't a constant, it's actually zero. So what that means is, for translational motion, the net forces acting on the body, which is also dp dt, is equal to 0 in equilibrium. And for the rotational aspect, the net torque acting on the body, which is dl dt, has to equal 0. For simplicity, we'll assume that all the forces act in the xy plane. Therefore, all the torques will be in the z direction, or parallel to the z-axis. This gives us then our equations of equilibrium. Which are that net force in the x direction equals 0, net force in the y direction equals 0, and the torque, net torque in the z direction is equal to 0. And these are what we will use to solve problems. For most cases, the gravitational force G is the same throughout a body. We then find that the gravitational force, F sub G, acts at a single point in the body, its center of gravity. Which, in this situation where G is the same throughout the body, is the same as the center of mass. To make it easier when solving problems of equilibrium, we can choose an axis of rotation for the torque that goes through the origin of an unknown force, which eliminates that force in our calculations. That's because the torque at that point would be 0. So if you have a bar and you have forces on it, and these are both unknowns, instead of putting the axis of rotation for the torque through the center, you can choose putting it through one of the forces, and in that case the torque will be 0 because torque is R cross F and R is 0. So that's just a simplification when solving problems. Now let's look at elasticity. Elasticity describes how a body deforms when forces are applied to it. There are three ways for a body to deform. The first is through tensile stress. And that's where a body is stretched or compressed. So you start out with a body and it could be stretched that way or it could be compressed. The second way is with a shearing stress. And that's where a body is shifted to the side. So you'll have a body that starts this way and ends up being pushed that way. And the third way is hydraulic or bulk stress. And that is where a body is compressed to a smaller volume. So you start with a body of that volume, and that ends up with that volume. I mentioned the term stress. Stress is the force that causes the deformity or the strain of the body. They are proportional through a constant of proportionality called the modulus of elasticity. So stress, which is actually the force applied, is equal to the modulus times the strain. And stress is actually force per unit area. As stress is applied and a body deforms, it will recover to its initial form up to its yield strength, given as S. After this point, the body will be permanently deformed. This is the point of plasticity, and the body won't return to its original form. If the stress continues to increase, the body will fracture or rupture. This is the tensile strength point, also known as the ultimate strength point, given as S sub U. Now let's look more closely at the three types of deformation. So we have our tensile stress. And again, that causes stretching or compression. So if you have a rod or an object or a block, and this is area A, the force applied is perpendicular to the surface area, up or down. So it's perpendicular to A. And tensile stress, again, is force per unit area. And the strain is the change in length over the initial length, because we're either compressing or stretching the body. And these are related by Hooke's law, which is force equals E times delta L over L, where E is Young's modulus. And E is sometimes given by the letter Y as well. And the unit of measure of stress is in pascals, given as PA. And also these are newtons per meter squared. And can also be given as PSI, pounds per square inch. So in this equation, this would be stress. This is the actual strain. And that's the modulus, in this case, Young's modulus. Our second type of stress is a shear stress. And in this case, you have your body with the area A. But in this case, the force is applied tangent or in the plane of the area A. And that causes it to shift to the side. And you get a delta x, which is the degree that the object shifts. So our equation with under Hooke's law is equal to G delta x over L, where again delta x is the distance that our body shifts, and L is the length of the body. And G, in this case, is equal to the shear modulus. And that's sometimes called S. I'd like to point out one little mathematical trick. So if you have a body and you shift it over by an angle phi, and this is delta x and this is L, usually delta x and phi are very small. And in that case, delta x over L is equal to the tan of phi. And for very small angles of phi, delta x over L is actually approximately equal to phi. We're talking about less than 1 degree, which would mean then that delta x is equal to L times phi. If we then go back to our equation, we get F over A is equal to G times L phi over L, or F over A is approximately, these are approximates, G phi. And this is in radians. So you can use this trick to find phi, the angle that the shear stress causes, for very small movements. Our third type of stress is hydraulic, also called bulk stress. And that is where you have an object and you have pressure on that object all around, and that causes the volume to shrink. And in this case, F over A we call pressure is equal to the hydraulic modulus times the change in volume over volume, where B is the bulk modulus. P is, again, force per unit area, and delta V is the change in volume. Now, the units of stress in this case, which is the pressure, are again pascals, or they could be atmospheres, ATMs. That's used a lot when it comes to depths of water. And I just want to point out that in this equation, as the pressure goes up, the volume decreases, so very often we end up with a negative result. So just bear that in mind. And one last thing I'd like to mention is that the reciprocal of the bulk modulus, B, is called the compressibility factor, or K. And again, that's just a reciprocal of B. So K is equal to 1 over B, which will be equal to the change in volume over V delta P again, using this equation. This gives the fractional decrease in volume, delta V over V, per unit increase in pressure that a body undergoes. And the units for that are 1 over the Pascal, or atm to the minus 1. Let's do some problems starting with equilibrium. The first one is a bar of length L and mass M is attached to a wall. What are the forces exerted by the bar on the wall? So let's do a diagram. Here's our wall. This bar is attached to the wall. So that's attached here. And we'll call the length L. So this would be L over 2 as far as the length. And we have the weight of the bar, mg. And we're going to make our axis of rotation over on the end away from the wall. So the forces in the x direction, there are none. So let's look at the forces in the y direction, which have to equal 0. So we have the force of the wall minus the force of the weight equals 0. So the force of the wall is equal to mg. And now let's look at the torque. And so the sum of the torques have to equal 0. So we have the torque exerted by the wall minus the torque due to the weight, which is mg, times the distance from the rotation point times L over 2 has to equal 0, or the torque of the wall is equal to 1/2 mg L. So these are the forces exerted on the wall. The force of the weight of the bar and the force of the torque of the bar. Here's another equilibrium problem. A ladder of length 5 meters and mass 12 kilograms leans against a frictionless wall. The base of the ladder rests on a floor which has a coefficient of friction mu sub s equal to 0.4. The ladder makes an angle of 60 degrees with the floor. What is the maximum distance d a 70 kilogram person can climb up the ladder before it slips? So let's diagram this problem. We have our wall, we have our ladder, and that's at 60 degrees. We have the midpoint of the ladder where we have the weight of the ladder, which is the mass of the ladder times g, and we have a person going up the ladder that has a mass, a weight of the mass of the person times g, and the distance up the ladder is d that he can climb. And we know that the total distance for the ladder is 5 meters. Now let's look at the forces, the other forces that we have. You have a force of friction of the floor on the ladder. You have a normal force of the floor on the ladder. And you have a normal force of the wall pushing on the ladder. Call that Wn. And we know the mass of the ladder is 12 kilograms, and the mass of the person is 70 kilograms. So we're going to put our axis of rotation here, because then we can eliminate Fn and Fs to make our calculation easier. And we also know that the force of friction is equal to the coefficient of friction times Fn in this case. So let's look at our equations of equilibrium. So our transitional forces, that would be in the x and y direction, and call this x and y. So for x, we have force of friction minus a normal force of the wall is equal to 0. Those are the two forces in the x direction. Or the normal force of the wall is equal to Fs, which is equal to mu sub s times Fn. That's what the force of friction is. Now let's look at what's going on in the y direction. In this case, we have the normal force of the floor pushing up on the ladder minus the weight of the ladder, which is ml times g, minus the weight of the person, which is mp times g, has to equal 0. Or we get the normal force is equal to mlg plus mpg. And if we substitute the values in that we know, that is equal to 118 plus 686, which is equal to 804 newtons. That's our normal force of the floor pushing on the ladder. And if we go back and look at frictional force, that's equal to normal force of the wall, which again is coefficient of friction times the normal force of the floor, which is equal to 0.4 times what we just found, the normal force, that's 804. So our frictional force is equal to 322 newtons. And we're going to say that this is the maximal point before the static friction slips and the ladder moves. And so that's what Wn is. This is the maximum frictional force we can obtain from the weight of the person on the ladder. Now let's look at our torque. And we know the sum of torque has to equal 0. And we placed our axis at the base of the ladder, so we don't have to include normal force of the ladder or the force of friction in the equation. So what do we have? We have the torque of the person trying to rotate the ladder down, and we have the torque of the ladder trying to rotate the ladder down, and the torque of the wall, which is going to be in the opposite direction. So in this case, we have the torque of the ladder plus the torque of the person minus the torque of the wall has to equal 0. And this becomes the weight of the ladder, which is m sub gl, times the distance that the center of gravity of the ladder is from our axis point, which is 1/2 L cosine theta, plus the weight of the person times that distance, which is d cosine theta, because if you go back up here, here's d, and here's cosine theta, and this would be the torque. So that's d cosine theta, okay, minus the torque exerted by the wall, which is Wn times L sine theta, has to equal 0. So we can put these amounts in. So we have the weight of the ladder times 1/2, and the cosine of 60 degrees is 0.5, plus the weight of the person, 686, times d, times the cosine, which is 0.5, minus 322, times the length of the ladder, which is 5 meters, times the sine of 60, which is 0.87, equals 0. And if you go through the math, you get that d comes out to be 4 meters. So that's the distance, the maximum distance the person can climb up the ladder before it overcomes the force of friction and it slips. Now let's do some elasticity problems. How much force is needed to stretch a 2 centimeter diameter rod by 0.01%? Young's modulus for the rod is 200,000 megapascals. So we know from our equation of Hooke's law for elasticity, force over area is equal to Young's modulus times delta L over L, or force is equal to area times Young's modulus times delta L over L. And I like to point out that Young's modulus is very often given the letter Y, but is also very often used as the letter E. So either one would apply. So if we substitute what we know into this equation, area is pi times r squared, which would be 0.01 squared, times E, which is 200 times 10 to the 9th Pascal, times delta L over L. And we want 0.01%, which is 10 to the minus 4th times L over L, where these, L, where these cancel out. So that ends up being equal to 628 times 10 to the 1 newtons, or the force is equal to 6,280 newtons. That's the force needed to stretch the rod by 0.01%. Here's our next problem. What is the minimum diameter of a rod if it is to support a 500 Newton load without exceeding its yield strength? Assume that the stress limit for this yield strength is 400 megapascals. Well, we can find the minimum area to find the diameter. So we know that stress is defined as force per unit area, and in this case we know the yield strength the yield stress is 400 megapascals. So area is equal to force over 400 megapascals from this equation, which is equal to the force is 500 newtons over 400 times 10 to the 6 pascals. So we end up with an area is equal to 1.25 times 10 to the minus 6 meters squared. And we also know that area is equal to pi r squared, which is equal to pi d squared over 4, or d squared is equal to 4a over pi, which is equal to 4 times 1.25 by 10 to the minus 6 over 3.14. D squared comes out to be equal to 1.59 times 10 to the minus 6, and d is equal to the square root of that, which is equal to 1.26 times 10 to the minus 3 meters, or 1.26 millimeters. So that is the minimum diameter of the rod needed to support the 500 Newton load. Let's do another shear problem. A force of 3,000 newtons is applied to a metal block that is 25 centimeters on a side. Find the angle and distance of displacement that occurs. The shear module for the block is 80 gigapascals. So we have a block, and the block is 25 centimeters per side, and a 3,000 Newton force is applied, and that moves the block over a distance of delta x, and we're kind of exaggerating that distance in this diagram. So we write down our equation. Force over area is equal to shear modulus times delta x over L. And as described earlier in this video, if we look at this part right here, you have L, delta x, and let's call that theta, then the tan of theta is equal to delta x over L. So if we substitute this in here, we get F over A is equal to G times the tan of theta. And as also discussed, for very, very small displacements and small angles, tan theta is approximately equal to theta in radians. So if we substitute that in this equation, we get F is equal to G theta approximately. And if we solve for theta, that's approximately equal to F over GA, which is equal to 3,000 newtons over G, which is 8 times 10 to the 10th pascals, times the area, which is 6.25 times 10 to the minus 2 meters. And theta then becomes 6 by 10 to minus 7th radians. So that's the angle that is displaced. And we want to find the distance. So again, we know that from this equation, tan theta is equal to delta x over L, or because this is a very small displacement, theta is equal to delta x over L. So delta x is equal to theta times L, which is equal to 6 times 10 to the minus 7th radian times L, which is 25 centimeters, or the displacement comes out to be 1.5 times 10 to the minus 5th centimeters. And lastly, we'll do a couple of hydraulic or bulk stress problems. What pressure is needed to decrease the volume of 300 liters of water by 0.003%? The bulk modulus for water is 2100 megapascals. So let's write out our equation, and that is pressure is equal to the bulk modulus times the change in volume over volume. So that's equal to the bulk modulus, which is 2.1 times 10 to the 9th pascals times 3 times 10 to the minus 5 times the original volume, which is 300 liters, divided by 300 liters. Well, those cancel out, and that's equal to 6.3 times 10 to the 4th, or the pressure is equal to 63 kilopascals.